This is Miss McClellan here to go over a supplemental addition to IM2 Notes for Chapter 9.1. This is graphing quadratics using the 1, 3, 5 method. We have two learning goals. The first is that we'll write these in the first person. I will be able to differentiate between the slope of a line and the rate of change of a quadratic function. And two, that I will be able to efficiently graph parabolas from graphing form using the 1, 3, 5 method. Let's get started. Exercise number 1, exploring average rate of change. We consider the quadratic function y equals x squared, and we'll fill in a table of values for the function and plot its points. Okay, so y is x squared. So I'm going to square these values to get y. Negative 2 squared is 4, negative 1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. Let's plot these points. Okay, negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4, connecting with a smooth curve. All right, we're going to use the table of value, and we'll be calculating the average rate of change between the following points in the parabola, between 0, 0, and 1, 1. So we'll be using change in y over change in x. So we'll have 1 minus 0 over 1 minus 0, which is 1. Next, uh, 1, 1 to 2, comma 4. So we'll do change in y over change in x, and that equals 4 minus 1 over 2 minus 1, which is 3 over 1, which is 3. And visually, I can agree with that because I go over 1 and up 3, which is the slope of 3. Okay, next, this one's not on the graph, so we'll just have to rely entirely on algebra. 9 minus 4, change in y, over 3 minus 2, change in x. This equals 5 over 1, which is 5. Okay, these numbers, 1, 3, 5, are going to be very important. So there's a reason we're asking you to find the slopes between these points in particular. Let's describe any patterns we observe in the average rate of change at 1 x unit intervals, meaning that we're taking these 1 x unit intervals every time I go over 1. What's going on with how much I go up? Well, first I go over 1, up 1. Then I go over 1, up 3. Then I go over 1, up 5. 1, 3, 5. I notice that the change in y is increasing each time. I'm going to just say that I predict next time I went over 1x, I would have gone up 7. 1, 3, 5. Yeah. And then I think I'd get 9. And then I think it would be 11. I think it's increasing as my odd numbers. Let's continue. This is the pattern. We're going to use this to graph a bunch of parabolas. Okay, first parabola. We're going to identify the vertex using h and k. That's from our last notes. So here, given that the normal formula is y equals a x minus h squared plus k. Here I have h is 4. K is -6, and my vertex must be at 4, -6. My a value is just 1, because 1 times that would be x minus 4 squared again. Now we're going to plot the vertex. I go over 4, down 6. And then I'm going to use a rate of change pattern. So what that means is I'm going to use the fact that the shape of the parabola will have a very predictable rate of change. First, I'll go over 1x, and then I'll go up 1. Then I'll go over 1x, and up 3. Then I'll go over 1x and up 5. Let me count 2, 5. And using symmetry, I'll do both sides of my graph. Okay, I will connect with a smooth curve. And that is the graph. This is the graph of my function y equals x minus 4 squared minus 6. Okay, next problem. So this one says, Sonia was asked to graph the quadratic function y equals 2 x minus 3 squared plus 1. However, when she plotted the points on the graph, her parabola didn't look quite right. She noticed that her graph was wider than she expected, and she realized she might have made a mistake in her calculations. So, this is Sonia's graph, and I think it looks good. I mean, she's got the vertex right. The vertex should be at 3, 1. And then she's using that same step pattern, over 1, up 1, over 1, up 3, etc. But for some reason the computer gave this graph, and it does look more narrow. I agree. Well, I think I know the mistake. I'm going to analyze Sonia's work and determine what errors she made when graphing the function. And the error that she made has to do with the fact that her a value is not 1. She has a equals 2. So her graph should be stretched vertically by a factor of 2. So based on the value of a, this is going to be stretched vertically. What I'm stretching vertically is my vertical step pattern. Vertically, on a parabola where a was 1, I would go up 1 and then 3 and then 5. But this is stretched by a factor of 2. So I'm going to multiply 2 into the step pattern. So I should have gone up, she should have gone up 2 and then 6 and then 10, which is what she did. Which is what the computer did. The computer went over 1, up 2. Then over 1, up 6. Let's just double check. Yeah. So that's the problem. She needed to double all of the values in her step pattern. So she needed to multiply all the values in her step pattern by 2, because that's what A is. Okay, let's do some practice. We're going to use our rate of change pattern and vertex to graph this parabola. So I've got h is 4. This is based on y equals a x minus h squared plus k. So h is 4 and k is -6. So my vertex is at 4, comma, -6. A is 2. So I'll plot the vertex. It's at 4, -6. And then I'm going to figure out my step pattern for this particular parabola, which depends on A and my original step pattern. So I'll do 2 times 1, 3, 5, which gets me my step pattern is 2, 6, 10. I go over 1, up 2, over 1, up 6, 6, and then over 1, up 10, but I don't have room for that. Okay. I'll use symmetry, and then I'll connect my points with a smooth curve. Smooth curve. Smooth curve. I live in Smooth Curve City. Have you been there? Continuing. 4a. Let's explain the difference between the constant rate of change in a linear function and the average rate of change for a linear function is what we remember as slope. y1 minus y2 over x1 minus x2. And a key feature of lines is that no matter what points you pick, you get the same value for slope. This is not true for our new friend, the quadratic, which has differing rates of change depending END ING depending on what points you use. And that difference turns out to be something that comes up a little bit in calculus. Okay, how can the rate of change pattern and the vertex help us graph a parabola more efficiently? Well, now all we need is a vertex and an A value, and we can graph any parabola using the rate of change pattern which we will often refer to as 1, 3, 5, period. Let's do some practice. So for each of these quadratics, we're going to identify the vertex, identify A, plot the vertex, and then use our pattern to get the next 4 points in general. Okay, so here we have y equals x minus 3 squared plus 1. This is using the graphing form, so I'll write that here. Y equals ax minus h squared plus k. Our vertex is going to be at hk, which is 3, 1. Remember that h changes sign kind of. It doesn't really, because we have minus h here, so h is just 3, but sometimes it helps to think of it as changing. Anyway, a equals 1, so my pattern is going to be 1, 3, 5. I don't have to multiply by anything. Let's go over 3 up 1 on my graph, and then use my rate of change pattern to get 4 more points. There's my vertex, 3, 1. Now rate of change. I go over 1, up 1. I go over 1, up 3. I go over 1, up 5. And then I have symmetry to get the other parts. And I connect with a smooth curve. If you can find the vertex and you can identify A, graphing is a breeze with 1, 3, 5. Okay, next. Now I have h and k are 2 and 4, so my vertex will be at 2, 4. And A is not 1, A is negative 1 this time. So A is negative 1, so my step pattern will be negative 1 times 1, 3, and 5 equals negative 1, negative 3, negative 5. So instead of going up, I'll go down. Okay, I start with my vertex. Now I'll do my step pattern. I go down 1 over 1, negative 1, then negative 3, then negative 2, 5. And then I use symmetry to get my other points. Okay. Smooth curve. And next problem. Okay, I have hk. H is negative 1. K is negative 3. A is 2, so my step pattern will be 2 times 1, 3, 5, which is 2, 6, 10. Start with the vertex at negative 1, negative 3. And now I'll use my step pattern. So I go over 1, up 2, over 1, up 6, 6. And again, with symmetry. Okay. I can do that better. Smooth curve. There, next problem. Okay. H and K, that's negative 4, positive 2. I have A equals negative 0.5. I multiply that by 135. And I get negative 0.5, negative 1.5, and negative 2.5 as my step pattern. So I start with my vertex at 4, negative 4, 2, and then I go over 1, down 1/2, over 1, down 1.5, over 1, down 2.5. So minus 0.5, minus 1.5, minus 2.5. And I do that symmetrically as best I can. Okay, smooth curve. All right. Next, h and k, I'm at 5, comma, -6. A is 3, so I plot A times my 135, which means I'll be doing 3 times 135. 3 times 135, so that's 3, 9, 15. I'll start with my vertex at 5, -6. Down here. Okay, and then I go over 1 up 3, over 1 up 9, 7, 8, 9. And I do that symmetrically. And I connect with a smooth curve. I find narrow parabolas to be difficult to graph with a smooth curve, but I always make sure that it's not pointy. I cannot have a point at my vertex. It's important that the parabola is not pointy at the vertex. I should have been labeling these vertices. This is 5, -6. The previous one was -4 up 2. The one previous to that was -1, -3. And the one previous to that was 2, 4. Okay, next problem. My vertex is at -3, 5. A is equal to -2, so my step pattern will be -2 times 135, which is -2, -6, -10. Start with my vertex, which is at -3, 5. 3 and 5. Then I go down 2, over 1, down 6, and I do that symmetrically. Smooth curve. I encourage you to pause the video now and try the next 3 problems. Never mind, I don't, because it's not obvious. I have to remind you how to find the vertex for these. So these are written in standard form, and to find the vertex from standard form, we used to factor, find x-intercepts, and go in the middle. We're not going to do that anymore. The vertex has an x and a y component. The x part of the vertex and the y part of the vertex. It happens to be that the x part of the vertex is equal to -b over 2a, where a, b, and c are from the parabola written in standard form. Y equals ax squared plus bx plus c. So for this graph, my vertex is at negative times -4 over 2 times 1. So that's 2. And then to find the y part of my vertex, I plug 2 into the equation. So y part of my vertex will equal 2 squared minus 4 times 2 plus 3, which is -1. So my vertex is at 2, -1. And a is equal to 1, because that's what it is in my equation. So my step pattern will be 1, 3, 5. I plot my vertex, I use my step pattern. Over 2, down 1, and step pattern. 1, over 1 up 3, over 1 up 5. And symmetry. Okay, and then this is 2, -1. Now you could have factored this and found the middle. It is factorable, but I like this method, and this is the method that we're learning today. Okay, next problem. Let's get our vertex. The x part of my vertex is at negative b over 2a. Here I have b is 8, so this is going to be negative 8, and a is negative 2. 2 times negative 2, which is negative 8 over negative 4, which is positive 2. The y part of my vertex is going to be at negative 2 times 2 squared plus 8 times 2 plus 4. So that's negative 8 plus 8 times 2, which is 8 plus 4 is 12. That can't be right. Just a moment. No, it's definitely 12. I'm just going to have to be creative when I graph this. Okay, so our vertex is at 2, 12. And our step pattern is, since a is negative 2, going to be negative 2 times 1, 3, 5, which is negative 2, negative 6, negative 10. All right, because this graph in the notes doesn't fit the number 12 on it vertically, I'm going to change my scale. I'm going to make this be 3, and I'll go up by 3s instead of 1s. 3, 6, 9, 12, negative 3, negative 6, negative 9, negative 12, negative 15. And now my graph will fit. But it's not going to look the way you expect it to look because of the fact that the graph itself is compressed. Okay, I go over 2 up to 12. This is my vertex. Then I use my step pattern to plot my point. So I go over 1, down 2, which will be to about here because all the way down to the next lattice point would have been down 3 since my y scale is now by 3s. Okay. Then I go down 6, so I go over 1, down 6, which will take me to about here. Then I go over 1 and down 10, which will take me to here. And then I use symmetry. And I connect my points with a smooth curve. There you go. Okay, last problem. All right, the x part of my vertex will be at negative b over 2a. That's going to be negative of negative 6 over 2 times 3, and this will become positive 1. The y part of my vertex is going to be at 3 times 1 squared minus 6 times 1 plus 2, which is 3 minus 6 plus 2, which is negative 1. Oopsies. So my vertex is at 1, negative 1. My a value is 3. So my step pattern will have 3 multiplied by all its values. 3 times 1, 3, and 5, which will be 3, 9, 15. Okay. My vertex is at 1, negative 1. Okay. Go over 1, up 3. Go over 1, up 9. See? Very sensitive screen. Okay, connect with a smooth curve. Smooth, not pointy. Okay, wonderful students. That was the last problem. Hopefully, You know the difference between constant rate of change for a line and average rate of change for a quadratic. Basically, it's just that for a quadratic, the slope changes depending on which points you use. And for a line, no matter what points you pick, you're always going to calculate the same slope when you do change in y over change in x. Hopefully you are also comfortable using the vertex and the 1-3-5 method to plot parabolas. Make sure you do your homework to practice, and I'll see you next time. You're wonderful. Bye.